We're down a person. Let's go.
I did that, but then it like.
All right. So we left off last class. I believe we went over the complement rule, right? This is where we kind of left off. Where we said if we thought about the entire stream of outcome space, if we took the probability of an event, we added to it the probability of its complement. Well, that is everything. That's every possible outcome we could see. Those have to add up to 1. And once we said they had to add up to 1, if we rearrange it a little bit, we know that the probability of a complement is simply 1 minus the probability of an event. Or vice versa, the probability of an event is 1 minus its complement. Probability of its complement. And correct me if I'm wrong on this. I don't think I am, but I also know we looked at contingency tables. We talked about identifying. We talked about identifying the totals were the probability of the events themselves, and these top 4 left cells all represented what? Remember what those top 4? The intersections of whatever the row and column headings were, right? Wherever those events were at the row and column. So, that's kind of where we left off. Started talking about order doesn't matter when we're looking at the union or the intersection, complement rule. The final rule we have is this addition rule. Okay? So I think I glossed over something last class. Let me see if I'm going to change this to the order of the slides. Okay, yeah, I did. So that was good. I actually did this right. So the other rule we have is the union of 2 events is adding up the probability of each event and then subtracting its intersection. So why are we doing this? Well, if you think about the union means it can be an A, it's an outcome that's in event A, it could be an event B, or it could be in both. Right? So anything in this white space here represents the union of A and B. Right? All the outcomes that are in A and B or in both. The problem is I can't simply add the probability of A to the probability of B, because if I add this to this, I've double counted what's ever in both of them, right? So I don't want to double count those outcomes. So what I'll do is, because I know I've double counted them by simply adding up those probabilities, I'll subtract out the intersection, and now I've only counted it once. If I've counted it twice and I subtract it out, I've only counted it once. There's another way we can think about this. I guess I'll draw it out here. So you could think of it as, so we've got, here's A, here's B. This like crescent moon here is everything that's in circle A, but also not in B or B complement, right? It's another way of thinking about that area. We then also have this crescent moon over here, which is the probability of being in circle B, but not in A, right? Every outcome here is in circle B, but it's not in A, okay? So in B and not in A is basically a complement. Are we okay with, understand what I'm saying here? Why those are the way they are? Are there any questions on that? Okay. And then the only thing we're left with is this area in between, which is what is in A and in B. So, you know, this is okay. This is probably the easiest way to do it when we start working with the probabilities. If you want the union, add up the probability of each event and subtract the intersection. But we're using contingency tables. Another way you can find it is, well, you have these 3 areas, right? You broke it down, just add them all up, right? So kind of have them floating all over the place, but if they're on the same line, I'm just adding them all up. Okay? So let's look at my contingency table. Let's say I want the union of event A and B. I can do this 2 ways, right? So the first way, you could use this equation, right? Just add up the probabilities of the 2 events, subtract out the intersection. So here, what's the probability? I'll write it down and I'll start asking. So the union of the 2 events should just be sum of the 2 events minus the intersection. So what's the probability of A here? So we said the totals represent the probabilities of the events. So if I want the probability of A, 0.6, what would the probability of B be? Yeah, right, same kind of idea. Just go down to that total, 0.5. What's the probability of the intersection of those two things, A and B? Yeah, right, the intersection of A and B is right there. So we get what? 1.1 minus 0.4, 0.7. I could have also taken those three components over there, right? So the probability of A and B complement plus the probability of the intersection of those two events plus the probability of, what did I say, B and A complement. What I told you is true, that will also give us the right answer. Right? Now, visually, what that's going to look like is actually these three guys right here. Notice, what's the probability of A and B complement? 0.2. Probability of A and B, 0.4. Probability of B and A complement, 0.1. Right? So we actually, right, plugging in those values, and sure enough, we get the exact same answer. So there's two ways to do this on a contingency table. This way is not, it's the easier way to make mistakes and also not like the most technical way of finding it. You can basically, if you ever want the union of two events, go to the intersection of those two events, make an L and add those up. Right? So if I wanted the union of A complement and B complement, I would go to the intersection, make an L, add them up. That is not a great way to remember this in terms of like technical. The reason why that works is because of the way the contingency table is displayed. That will always kind of give you those three components of like that union space. You can like break it down into components. It would always be those three spaces. The easier way, I think, and the more technical way to do it, and the way that kind of moving forward will make the most sense when we're doing other things, right, is taking event B, add to event A, and subtract out the intersection. And that's wrong. I don't want that there. I want a, I must have clicked on the wrong one when I was inserting this. So let me move this. Symbol. Where's my set symbols? Oh, no, I'm not gonna be able to find it real quick. Oh, here, got it somewhere else I can copy and paste. All right, that's the intersection. So let's make sure it's labeled correctly. Okay, so we had two different ways of finding the union. Like I said, I think this is probably the better way to do it. Okay. Any questions on that before we keep moving? So it's not too bad. Kind of definitionally, kind of makes things easier for us. But if we have two events that we say are mutually exclusive, I think I might have already used this terminology when we were talking about building the bins for frequency distributions. But we would say two events are mutually exclusive if they can't happen at the same time. Right? So, you know, I can't be older than 60 and younger than 18. Right? I can't be in multiple categories, right? If I'm breaking this down into bins. Same idea here. If I have two events, they're mutually exclusive if there's no overlap, right? So they have no shared outcomes. So this would, on a contingency table, the only way that you know they're mutually exclusive is you see 0, right? At the intersection of these two things is 0. There's no overlap. Visually, right? This would be two circles with no overlap, right? Well, that makes life easy for us because now when I want to find the union of two events, well, if there's no overlap, I'm not double counting anything. I don't have to subtract out my intersection. Right? I mean, I can, but when I plug in the value, it's just me subtracting 0. It's not going to change anything. All right, so we have mutually exclusive events. Oops. Kind of simplifies finding the union where you just have to add the probability of the events. Right? Does that make any questions on that? Something in sense? Shouldn't be too bad. All right. So, where are we at? I don't want to run out of time. I want to go through some interesting examples. So I think I'll go over this pretty quickly. So I might skip some of the questions, but I will go through why this equation is what it is. So let's say my black more. So if I think about these, I guess for now, just believe me. This is what it is. I'm going to show you in a second. But what does this white area represent? That's the union of those two events, right? If you believe me for a second that this blue area, the area outside of those circles, is the intersection of those events' complements, right? Those two things would have to add up to what? It's the entire instrument from space, so it should add up to 1. So I know that if I take the probability of the union of two events and add to it the intersection of the complements of those events, like I said, I'll can give you some support of why that blue area is that, but for now, taking it my word, those have to add up to 1. Well, notice for the union, I said another way I can write that is just take the probability of each event, add them up, and subtract out the intersection. So anytime I have 3 of these 4 probabilities, I can always solve for the 4th one. I can solve for the unknown. More often than not, we're probably going to know these 3, and we're going to have to solve for the intersection of the complements. But if I have any 3 of these, I can solve for the unknown. So a little bit of support as to why that's the intersection of the complements. Just so you don't have to take me at my word. So we've got so here's my event A. And here's my event B. I'm going to use the blue area here to represent B complement. Right? I'm then going to use the red area to represent A complement. So A complement would be that red area. So the intersection of the complements here will be anywhere where this shaded blue and shaded red area kind of overlap. Well, notice here, that's just blue. Here, that's just red. The only place where they overlap is all the area outside of those 2 circles. Right? So the intersection of the complements, right, where they overlap, that's always going to be the area outside the union of those 2 events. Is that how I make it a little bit clearer why that's what it is? But really, at this point, it's just algebra. Right now, if I give you 3 of these, you can always solve for the 4th. Right? So, I think I've got some problems we'll skip through because I do want to do some more conditional probability stuff today. So we'll probably revisit this on Monday and work through some problems where we only have 3 of the 4 pieces of information and get an idea about what those problems look like. But today I want to focus a little bit more on thinking about the multiplication rule and thinking about, excuse me, conditional probabilities. So right now, I'm telling you that this multiplication rule will always hold. So when we said we had a conditional probability, I said last class, I'd hold off on discussion too much until we were actually talking about probabilities, not just the events themselves. So this would be something like, if I had 2 events, A and B, the probability, that somebody, is over 7 feet tall is relatively low. I don't know what it is, but it's very small. Right? But if I tell you, given that event B has occurred, and event B is that the person is in the NBA, the probability they're over 7 feet tall has changed dramatically, right? So my conditional probability and my unconditional probability, when I didn't have any information, could be very different. Right? So think about, try to draw an extreme example as to why. So that conditional probability we can think of is going to let us also be able to calculate the intersection. So if I've got the probability of A and B, this is the conditional probability multiplied by whatever I'm conditioning on. Right? So that's just what I have up here. So why does this hold? Right? Well, I'm thinking about this might look like visually. Actually, I think what I might do is, before I draw this, so this is the end result that we use a lot. If I rearrange this a little bit, I get that the conditional probability is just the intersection divided by what I conditional. Right? I think maybe this one will make a little more sense. So kind of introducing this idea, we'll rearrange that multiplication table, so our multiplication rule, so that we get the intersection divided by what I conditioned on. I think this one will make a little more sense. So let's say, so I know that A has occurred. So let's say this entire, instead of using circles, let's say this entire right side is event A. Right? And I'm telling you that the probability that A occurs is 0.5, or kind of like this area is 0.5. Right? I then have B, and B is just this area down here, right? And the probability that B occurs is 0.25. So the unconditional probability of B is a fourth, right? 0.25. There's a 25% chance it occurs. However, if I want to find the conditional probability, so given that A has occurred, now what's the probability that I see B occur? Well, that changes things a lot, because instead of the entire experimental outcome space, when I tell you that A has occurred, it's almost like your total area is no longer 1. The total area you're looking at is only 0.5, right? Whatever the probability that A has occurred was. So like your new denominator, like before there was kind of a denominator floating around that we ignored because the entire experimental outcome space was 1, right? The probability that occurred was 0.25 out of 1. But now that we have a conditional probability, now that I know I have to be somewhere in the space of A, my new entire space is not 1 now, but it's just whatever the probability of A was, 0.5. So now that I know that I'm in here, I know that of this 0.5 space, 0.25 of it is in B, right? So the probability I see B occur, given that I know A has occurred, would be 0.25 out of 0.5, intuitively. But notice, what do those areas represent? Well, that 0.5 was just the probability A occurred, right? Whatever I conditioned on, I no longer have an entire experimental outcome space of 1. My experimental outcome space is whatever the probability of the event that I'm conditioning on is. And then now, potentially, event B makes up a larger percentage of the space I'm left with than it originally did of the entire experimental outcome space. So now I'll look at what's left after I've conditioned on A. What are the outcomes that are left in B? What would be wherever A and B overlap? This is an extreme example where all of B overlapped with A, right? You can imagine I could do a different one where like maybe B had just slightly extended out here, right? And then instead of 0.25, maybe the probability of B was 0.3, but the intersection of A and B was still 0.25 or something like that, right? But I kind of drew it extreme to really point out that once you condition on something, you can dramatically change the probability of the event, like relative to the conditional probability. Notice here, the probability of B was no longer 0.25, the conditional probability of B rose to 0.5, right? And intuitively, this makes sense. If I have more information, I know things might be more or less likely to occur. I think, was it 2 semesters ago? I don't know if any of you have met Courtney. I think she's a senior this year. Yeah, so she's a special person. And I think we wasted 15 minutes of her trying to give me potential changes to this example. But I keep using it now because it makes me laugh. But I think last because I brought up about me going outside and slipping and falling, right? And that probability is relatively low. However, if you give me this additional piece of information that, given that it's freezing rain outside, what's the probability that when I walk out of the building, I slip and fall today? Changes dramatically, right? Anytime you have another piece of information, as long as those two events are somewhat related, it might dramatically change the probability, okay? So this is kind of the idea of conditional probabilities. This is the equation we can use to find them. So that I think makes a little bit more sense. But if we just rearrange things, right, we can end up having the conditional probability and being able to solve for the intersection of two, right? We're just rearranging that equation a little bit. So as long as I know two pieces of information there, I can solve for the third. So here's some of our rules. Excuse me. We'll start working through some more problems for both of these. We'll talk about independent events, not right now. I want to actually go through, did I have any? Oh yeah, so these are some actual problems that I wanted you to go through. So I think we'll hold off on this. I'll ask you guys to do it. Let you guys work with each other. So let's say, there we go, that I've got these events again. So R1, C2, and now I want the conditional probability of R1. So the conditional probability of R1, what are we conditioning on? We're conditioning on C2. So the way that we find these conditional probabilities will be the intersection of those two events divided by probability of what we're conditioning on. So give you guys like 2.5 minutes, kind of work with the people around you. Hopefully come up with the answer to this. Not too terribly tough. So you don't have to be quiet and talk to people around you.
I don't know, I'll let you say it was 2 years ago. I need some slack, right? Buzz in.
Oh yeah, whatever. Respond with whatever you think the correct answer is.
Yeah, I just want to make sure. Yeah, use the network.
It's not gonna tell me I'm wrong.
I know, I just want to make sure it's right on my head.
Okay, so the intersection, which is
Yeah.
divided by the second one, so the condition one. Yeah.
Oh, yeah. I'm going with that. I'm walking. We doing it?
We're doing it. There's a lot of points writing on it.
Sometimes I'll do something and it like unlocks in the middle, and I'm like he said something last week and I'm just like, I remember like the process test and I was like, I wasn't prepared for all this memory.
All right. So if you haven't gotten an answer in, take your best guess. We have 4, 5, 6, 7, 8, 9, 10, 13. All right, I think I got everybody in here. I'm going to close it out. All right. So if I'm writing this out, I want the probability of R1 given that I know C2 is a curve. So I'll write this out and follow the general form of my equation. So R1 given C2 should just be the intersection of those two events. So R1 and C2 divided by the probability of whatever I'm conditioning on. Remember, whatever I'm conditioning on, that's what I'm being told is true. So that's what my new space is limited to. I don't have the entire experimental outcome space of 1 now. I have whatever the area of event C2 was. Right? So we go up here, what the intersection of those two things is 0.2. The probability of C2 is 0.5. So I should end up with 0.4. Questions on that process? About exactly what order I'm going to do this in code. So, with this idea of conditional and unconditional probabilities, we also have this definition of independence. So, we say two events are independent if the conditional probability is the same as the unconditional probability, right? So that would be the probability of A conditioned on B is the same as the probability of A. Knowing that B has occurred doesn't change the probability of A at all. We would say that they're independent events. Kind of makes sense, right? The probability doesn't depend on this other thing, so they're independent. If they're not equal to each other, right, we would say they're dependent events. So remember, if I'm using this other form of that multiplication rule, right, where I just rewrite my conditional probability, like I just kind of rearrange things. If two events are independent, the conditional probability of A is the same as the unconditional probability. Or said differently, the conditional probability of B would be the same as the unconditional probability of B. So I could just plug in the probability of B here. So if I have independent events, their intersection, an easy way to find that, it's actually simply going to be the probability of those two events multiplied by each other. And I can check this pretty quickly in a contingency table. I can find this value in a cell. I can find these two values. If I multiply the probability A times the probability B, and it ends up being the probability of the intersection, they're independent. So we can do some independent checks here. There's also other ways we can check. We can be a little bit more, I don't know, thorough. I'll show you several different ways. So let's say we have this example. I know they're independent. The probability of A, and I don't remember if this is the one in the slide. So the one in the slide may be a little bit different, but the probability of A given B has to be the same as the probability of A. Well, to find a conditional probability, I know I can just rewrite this as what? The intersection of two events divided by, the probability of what I'm conditioning on, which is on the right-hand side, so the probability of B. So if this is the same as the probability of A, I know they're independent. So what's the probability of A here? No one? Let's not read this yet. What's right? The totals tell me the probability of the event. The probability of A is 0.6. I'm okay with uncomfortable silences. The probability of the intersections of A and B is what? What did someone say? Say it like you mean it. 0.15, right? And then the probability of B is
0.25.
There we go. That's what I want to hear. So 0.15 divided by 0.25 actually ends up being 0.6. So this is a situation where we would have what we would call independent events. It doesn't matter if I know that B has occurred, the probability of the conditional and unconditional probability of A is the exact same. So I did work through this as well. I had that up here. Oops. We could have also done it the other way, right? Instead of looking at the conditional and unconditional probability of A, I could have looked at the conditional and the unconditional probability of B. Now, if A and B are independent, it shouldn't matter which way I check it. They should, both should show me they're independent. So we just prove that this holds. So this should hold as well. We can work through it and prove that, right? So, let's skip through this. Oh no, I had it right here. So I could actually do this way where I looked at the conditional probability of B, which calculates to be 0.25. Well, what's the probability of B? 0.25. Sure enough, that way I would have found they were independent as well. The third way we said was if the intersection is equal to just the probability of A times the probability of B. So here, we can check to see if this is true. What's the probability of A and B? I think we just said that was what? That's 0.15. If that's the same as the probability of A times the probability of B, that would also show us they're independent. The probability of A is 0.6. Probability of B is 0.25. Sure enough, that way shows us they're independent as well. So 3 different ways of kind of checking to see the same thing. slides here as well, right? We just go through on that 0.15. Oh, excuse me. I forgot about something that's kind of interesting. I don't really use it or like expect you to remember it, but it is an interesting thing. If two events are independent, their complements will actually also be independent. So you could actually check the complements as well. So the intersection of the complements, right? A complement, B complement intersection is 0.3. If that's equal to the probability of A complement, which is 0.4 times the probability of B complement, which is 0.75, right? It should also show that they're independent. And so that's just another way of checking for it. It's probably a little bit trickier and hard to remember. I don't really ask questions on that, and so it should be okay. Any questions on this idea of independence? So it's a little bit different than being mutually exclusive, right? Mutually exclusive means these two events can't happen at the same time. We start to see intersections of 0. Independent just means that of the entire experimental outcome space, the same proportion of it is made up of event A as the proportion of the space in event B that event A makes up. So I'll give you, I want to make sure, okay. Oh, okay. So I'll give you a little bit of an idea about what it means if events are independent. Once again, I think I'll use squares here. So let's say here is, and I'm going to shade it just to make it a little bit easier to think about. Here's my event A. Okay. I'm then going to think about the second event, which is event B. So the probability of A, we'll say, is 0.5. And then I have event B, and it exactly splits it in half the other way, right? So I have the probability of A and the probability of B is 0.5. Event B makes up half of the entire experimental outcome space. But what if I think about what's the probability of B given A? Well, that's going to be the intersection of those two events divided by whatever I'm conditioning on. So what's the intersection of these two events? Well, these exactly split them in half. The crossover here in the lower right-hand corner would be 0.25. The entire, whoops, what am I conditioning on? Well, that's the entire area of A, which is 0.5. These are independent events because the probability of B given A is the same as just the unconditional probability of B. And why? Because of the entire experimental outcome space, B made up half of it. But when I condition on, well, I now know that A has occurred, well, the proportion of A that B makes up is also half, right? The area of A was 0.5, the area of that left of B was 0.25, and so it's still made up half of the entire outcome space left after we condition on something. So this would be like the idea of, if, you tell me something like, what's the probability someone is, I don't know, Republican, if you know that they're, 5'5" or over 5'5"? Doesn't matter. I mean, the distribution of height looks the same across political parties. Like it doesn't really, it doesn't tell me anything, right? And so having this additional piece of information, you haven't changed the makeup of the group that's left. Now, if I look like overall, I think I looked at the current study was something like in Indiana, 60% of people I think responded that they were in favor of marijuana legalization. So that out of everybody, if you choose one person at random, the probability that they support legalization of marijuana in Indiana is 0.6. But if I say, well, given that the person that you selected, that they are a registered Republican, what's the probability they want it legalized? Well, now, okay, the composition in the general public probably looks a little bit different on that issue when you're looking at the composition just within the Republican Party, right? So there are some, that would be dependent events, right? But if it didn't change at all, we have the kind of examples of independent events as well. The IQ question, I think we'll kind of come back to this on Monday. I'm going to show you some stuff in Excel. I'm just using Excel. A, because it's a little bit easier. I know someone's unfortunately not able to be here, so they can follow a little bit easier on what I'm working on my screen when they watch the video. But also, I like doing things in Excel sometimes. So just going to start with a blank workbook. And let's blow it up pretty big. So I need my cheat sheet here. So I was pretty proud of myself coming up with this example. So let's say we've got some events. So we're looking at individuals who have gotten COVID, right? So these are confirmed cases. I went out to the CDC. I grabbed some of their data, which is publicly available. And the breakdown, so I should say this, the CDC, I got this data from, and I'm rounding to the third decimal. So these are actually 0.010 and 0.990. So of the people that contracted COVID, 13% of them had been vaccinated, while 86% had been unvaccinated. Right? This is just the numbers from the CDC. Virginia then did this study where they kind of broke down deaths by these categories as well. So to be fully transparent, I grabbed the total data from the CDC. The other stuff came from Virginia, but assuming that the breakdown in Virginia looks like that of the rest of the country, that would be okay. So the probability that if you contract COVID, if I'm choosing someone, like I have this database of people who got COVID, like that's what the actual database looks like. I'm choosing someone out of it. What's the probability that they died from COVID and were vaccinated? So 0.001, probably they died and were unvaccinated, 0.009, probably they were unvaccinated and didn't die, 0.857, probably they were vaccinated and didn't die was 0.113, okay? So these should add up, if you're checking, double checking me, these should add up to the total, right? I could add across the rows or down the columns, and those should reproduce. So I could do a check here, make sure I didn't have a typo. If I add these up, I should get the 0.99. If I add across, pretty sure these are right. So this is my contingency table. I went and grabbed these probabilities from online. Let's think about, what if I wanted the probability that someone dies given that they're vaccinated? So if, looking at individuals who have gotten COVID, given that the person is vaccinated, what's the probability that they die, right? Well, this would be the same thing as, I don't want to put an equal sign here. So I can rewrite this as the probability of death and vaccinated divided by the probability of whatever I'm conditioning on. So what I'm conditioning on was that they were vaccinated. So you can kind of imagine the probability that someone kind of dies from COVID here. If the vaccine has any impact on reducing, the severity of COVID, we should see that these are not independent events, right? Being vaccinated should alter the probability of death just overall, which the probability overall was what? 0.01. Okay. So we can solve this, right? So what's the probability that of the individuals who got COVID, they died and were vaccinated? 0.001. And to be transparent also, it's actually a little bit lower than this. It was like 0.0008, but it was easier to show this at the third decimal. Divided by the probability that they're vaccinated. Well, the probability they're vaccinated of this, huge data set of individuals who have contracted COVID is 0.134. So the probability, right? Probability given someone's vaccinated, the probability they die is 0.00746. Okay. We could also do, what's the probability that, given that someone's contracted COVID, what's the probability they die, given that they are non-vaccinated? Oops. Right. So I could rewrite this as the intersection of those two events divided by now the probability of what I'm conditioned on. What I've conditioned on now is that they're non-vaccinated. Right? So what are these things? Oops. I have to zoom in a little less. So the probability that someone dies and is non-vaccinated in this data set is 0.009. divided by the probability that they're not vaccinated, 0.866. And we get a little bit higher of a probability there. So, these probabilities are relatively low. So even after you already get COVID, right, the probabilities that you die is 0.01, right? Right, so you got a 1% chance, I guess, but that's after you've contracted it. However, if you've contracted it and you're vaccinated, right, the probability that you die is falls a little bit. And the difference here, I don't know, if we're looking at percentages, right, what would this be? Well, we want to start with, this is our base, maybe we could think about. Oh, that's not what I want. Yeah, you can kind of, whatever, we'll just round these and I'll make the point. You can kind of see, so 0.0074 going up to 0.01, it's about 33% increase. So I think there was like 39%, I would subtract, it was 1.39, so about 39%, but roughly about a 33%, a third increase here. So by simply getting vaccinated, you can reduce your likelihood of dying by that much as well. You're getting unvaccinated, you increase your chances of dying by 33%, right? It doesn't matter which way I say that. So people get mad about these issues. I don't really understand. Like, we can just look like at the data, like we're saying here that this definitely looks like these aren't independent events, right? Now, can't say anything about long-term effects of the vaccine, or the whole discussion is maybe bigger than that. But in terms of whether or not dying after contracting COVID and the vaccine are correlated, like, we definitely can see that they are here. Right? If there's an effect, we can say these are definitely, not independent events. What else did I want to say here? We could actually go through, I worked through this for the hospitalization numbers too. And surprisingly, there actually wasn't as great of a difference here. Just, like I said, full transparency, the data, data is what it is. But for hospitalizations, it actually didn't look like there was a little bit of a difference from getting vaccinated, but not near as strong as when you look at the actual death data. So I thought that was kind of interesting. Any questions on this? Yes, I try to just use examples that are pretty relevant. So I thought this was an interesting one. I didn't know that Virginia data was out there that kind of broke it down, deaths and things by vaccination status. So I forget what exactly it's called, but if you Google search CDC Virginia COVID data, probably pops up. Is there anything else I would want to do here? I think that's it. So that's kind of a quick little example of how we use contingency tables to come up with conditional probabilities. We will next week start to build our own contingency tables. So something we haven't talked about up to this point is when I'm looking at these contingency tables, right? Where am I getting these probabilities from? Like, how did I just build that contingency table? Where did these probabilities come from? You can actually use the numbers, right? If I have the total number of people who had COVID, right? That was what that data set was. And then I have the total number of people who were vaccinated and then died. Well, the probability then, if I get COVID, that I was also vaccinated and I died, would be whatever the number of people who were vaccinated and had COVID were divided by the total number of observations. So all these probabilities could actually come from an original data set. Now, I'd have to go through and count the number of people who were vaccinated and died and then count the total number of observations. But we've been talking about this count-ifs formula. Just the count function gives us the total number of observations. So next week, we'll start using that count-ifs formula a little bit differently, and we'll actually build our own contingency table. So the file that I think I have up there on Canvas, there's one that just says probability tables. I don't know if I like that one as much. I'm going to try to give you a little bit more of a businessy example with this Excel, which is we've got some union data, right? So we'll kind of start out working with this on Monday and build our own contingency table. We'll save these for Monday as well, some different ones. But I think we'll do 5 minutes. We talked about independence today. This is kind of it's Friday. I'll save this until Monday. So I'll let you guys out a little bit early. We will kind of finish up our discussion about independence, how we build our own contingency tables in Excel next week. And then we will start moving on to some probably more difficult content like Bayes' theorem and things like that. So you guys have, wait. What current, you have Excel and Connect assignment due, right? On Monday? Right. Okay, so we talked about last class, number 14 does have an issue with it. So don't worry about it. I don't know. I think you can change the number of or the sample to population, and sometimes we'll still count it as wrong. So I'll just end up giving everyone full credit for that. All right. Have a good weekend.